Today, I will explain you how Monolix generates survival curves for time-to-event data and how we can visualize them in Monolix. Feature of the week number 13 presented how time-to-event data are formatted in Monolix. This type of data differs from PK or PD observations because here time itself is an observation. It can be a time of, for example, death of a patient or times of repeating seizures. A study can give us exact times or time intervals when events occur. In addition, patients can leave a study before experiencing an event. They can die due to other illnesses, or they might not experience an event at all during the observation period. One of the functions that play a key role in the analysis of time-to-event data is the survival function, which is denoted here by SFT. It describes the probability that an event happens after a certain time t. In general, the survival S is unknown, but a typical way to approximate it is the non-parametric Kaplan-Meier estimator. This is what is displayed in Data Explorer for time-to-event data. To explain the formula, notice first that the probability that an event occurs is the ratio between the number of events that occurred, denoted here by di, and the total number of individuals at risk, denoted here by ni. This total number are individuals who did not experience yet an event. The complement of this probability estimates the survival. Then, for each time t, we have to multiply probabilities calculated at all previous times ti when at least one event occurred. It is similar to calculating the probability that a patient survives 2 days. It is a product of a probability that a patient survives the first day and the conditional probability that he survives the second day, knowing that he survived the first one. Let's see now in practice how the Kaplan-Meier estimator is calculated on a typical time-to-event example. Here I defined a data set with 5 individuals who have 2 entries. A time when the observation starts, which is 0 for all individuals, and the time of an event. If a patient leaves a study, then the second entry is a time of a dropout. It is easier to compute the Kaplan-Meier estimator if I order the data by increasing time of events and dropouts, because at these points the survival curve can change shape. So let's calculate the Kaplan-Meier estimator step by step. A study starts at time 0, and at that moment there were no events. So d in the formula for the Kaplan-Meier estimator equals to 0, and the value of the survival function is 1. Until the next event time, so here t equal to 1, the survival function remains constant. Then at t equal to 1, one individual experiences an event, so d becomes 1. All individuals were at risk, so n is 5. If we put these values in the formula, we see that probability to survive decreased by 0.2. You can see it in the plot as a height of the jump of the survival function. Then again, until the next event, survival function remains constant. At the next time, t equal 3, there were 2 events. The total number of individuals at risk is now 4. It decreased by 1 due to the previous event. To get the final value of the survival function, we have to multiply the current probability by all earlier probabilities. At the next time, there is a dropout. Patient 5 left the study and no event was registered. D in the formula is now 0 and the survival does not change. A dropout time is marked with a red dot in the plot. An advantage of the Kaplan-Meier estimator is that it takes into account such situations where not all individuals continue a study, because at the next event time, such individuals will not be counted as individuals at risk and will not be counted in the denominator n. So here at time t equals 5, we have only one individual left and one event, so the survival function is 0. Now let's see what happens with the interval sensor data. For example, if observation started at t equal to 0 and event occurred at t equal to 1, it is impossible to distinguish without any other information if the event was at t equal to 1 or before. Or in another example, if we give a time when the study starts and time interval limits when an event occurred, for example, between 2 and 3, just looking at the dataset, we cannot select if we deal with an exact or an interval-censored event. This is why for data visualization in monoliths, we assume that all events are exactly observed. That is, not knowing when an event happened, we assume that it happened at the end of the censored interval. So in this case, for an individual one, an event occurred exactly at time equal to 1, and for the individual 2, an event occurred exactly at the time equal 3. The Kaplan-Meier estimator can be used also for the analysis of repeated events. The survival curve can be approximated for each kth event separately. In monoliths, we use it to calculate an average number of events as a function of time. Let's see how it looks like in Data Explorer. As an example, I use a study on patients with cancer who received two different treatments. I can visualize the survival curve for the whole population. Red dots here correspond to the data when a patient left the study. In the subplots, I can also visualize mean number of events per subject. In Data Explorer, stratification options allow to only split the Kaplan-Meier curve. For example, I can allocate treatment and use it to split the survival function. It is not possible to plot more than one survival curve on the same plot, but we can do it in monoliths. To do it, I will first save the project and export it to monoliths. To see the plots, I have to select any structural model. Because I'm interested only in the visualization of the data, I use monoliths time to event library and select the simplest model. So exponential without delay and single event. Initialization of parameters and running estimation task is not necessary, but I will save the project so that my plot settings will be saved. Now I will just run plots. And in the Observed Data section, I can visualize the Kaplan-Meier curve exactly as it was in Data Explorer. The difference with the Data Explorer is that in monoliths, I have additional option. So if I split the curve for two different treatments, there is another button, Merge, which overposes two curves on one figure. I can also add additional covariate, for example, Karnofsky score, and add it to the splitting part. To personalize further plots, you can export charts data for post-processing here. In this way, monoliths saves values of survival function for each splitting option that you have selected, and it's then easy to group and replot everything as you prefer. You find these results in the results folder of the project in charts data, observed data, events, empirical curves. You can find more information in our online documentation. Thank you for listening and take care.